Welcome back to my video series on machine learning in Scikit-learn. In the previous video, we went through the entire data science pipeline, including reading data using pandas, visualization using Seaborn, and training and interpreting a linear regression model using Scikit-learn. We also covered evaluation metrics for regression, as well as feature selection using the train-test-split procedure. In this video, I'll be covering the following. What's the drawback of using the train-test-split procedure for model evaluation? How does k-fold cross-validation overcome this limitation? How can cross-validation be used for selecting tuning parameters, choosing between models, and selecting features? And what are some possible improvements to cross-validation? Let's start by reviewing what we've learned so far about model evaluation procedures. One of the primary reasons we evaluate machine learning models is so that we can choose the best available model. The goal of supervised learning is to build a model that generalizes to out-of-sample data, and thus we want a model evaluation procedure that allows us to estimate how well a given model is likely to perform on out-of-sample data. We can then use that performance estimate to choose between the available models. Our first idea was to train each model on the entire dataset and then evaluate each model by testing how well it performs on that same data. This produces an evaluation metric known as training accuracy. Unfortunately, training accuracy rewards overly complex models that are unlikely to generalize to future data, which is known as overfitting the training data. The alternative procedure we came up with is called train-test-split, in which we split the dataset into two pieces, known as the training and testing sets. We train the model on the training set, and we evaluate the model by testing its performance on the testing set. The resulting evaluation metric is known as testing accuracy, which is a better estimate of out-of-sample performance than training accuracy because we trained and tested the model on different sets of data. As well, testing accuracy does not reward overly complex models, and thus it helps us to avoid overfitting. However, there is a drawback to the train-test-split procedure. It turns out that testing accuracy is a high variance estimate of out-of-sample accuracy, meaning that testing accuracy can change a lot depending on which observations happen to be in the testing set. Let's see an example of this in Scikit-learn using the iris dataset, which we've worked with previously. First, we'll import the relevant functions, classes, and modules. Then, we'll read in the iris dataset and define our feature matrix X and our response vector Y. In this next cell, we'll use the train-test-split function to split X and Y into 4 pieces. The splits are random, but I've set the random state parameter so that if you run this code at home using the same random state value, your data will be split in the exact same way as my data. We'll also instantiate the kneighbors classifier model with the parameter nneighbors equals 5, fit the model with the training data, make predictions on the testing data, and evaluate the accuracy of our predictions. The reported testing accuracy of our model is 97%. But what if we reran this code and the only thing we changed was which observations were assigned to the training and testing sets. If we change the random state parameter to 3 and rerun the cell, we get a testing accuracy of 95%. If we change the random state to 2, we get a testing accuracy of 100%. This is why testing accuracy is known as a high variance estimate. Naturally, you might think that we could solve this problem by creating a bunch of different train test splits, calculating the testing accuracy each time, and then averaging the results together in order to reduce the variance. In fact, that is the essence of how cross-validation works. Let's walk through the steps for k-fold cross-validation, which is the most common type of cross-validation. First, we choose a number for k and split the entire dataset into k partitions of equal size. These partitions are known as folds. So if k was equal to 5 and the dataset had 150 observations, each of the 5 folds would contain 30 observations. Second, we designate the observations in fold 1 as the testing set, and the union of all other folds as the training set. In the example I just mentioned, the testing set would contain the 30 observations from fold 1, and the training set would contain the 120 observations from folds 2 through 5. Third, we train the model on the training set, we make predictions on the testing set, and we calculate the testing accuracy. Then, we would repeat steps 2 and 3 k times, using a different fold as the testing set each time. Since k equals 5 in our example, we would be repeating this process a total of 5 times. During the second iteration, fold 2 would be the testing set, and the union of folds 1, 3, 4, and 5 would be the training set. During the third iteration, fold 3 would be the testing set, and the union of folds 1, 2, 4, and 5 would be the training set, and so on. Finally, the average testing accuracy, also known as the cross-validated accuracy, is used as the estimate of out-of-sample accuracy. Here's a diagram of 5-fold cross-validation that may be helpful to you. As you can see, each fold acts as the testing set for one iteration and is part of the training set for the other 4 iterations. One thing I want to make clear is that we are dividing the observations into 5 folds. We are not dividing the features into 5 folds. That might be confusing from the diagram, since normally we represent observations as rows, whereas this diagram represents observations as columns. I've written some simple code to demonstrate the process of splitting a dataset into folds. It's not important that you understand this code. Rather, I just want to focus on the output. Pretend that you have a dataset with 25 observations, numbered 0 through 24, and you want to use 5-fold cross-validation. This is an example of how that dataset might be split into the 5 folds. Each line represents one iteration of cross-validation in which the dataset has been split into training and testing sets. For each iteration, we can see the ID numbers of the 20 observations in the training set and the ID numbers of the 5 observations in the testing set. You'll notice that for a given iteration, every observation is either in the training set or the testing set, but not both. You'll also notice that every observation is in the testing set exactly once. Let's briefly compare cross-validation to train-test split to clarify the advantages of each. The main reason we prefer cross-validation to train-test split is that cross-validation generates a more accurate estimate of out-of-sample accuracy, which is what we need in order to choose the best model. As you've seen, it also uses the data more efficiently than train-test split, since every observation is used for both training and testing the model. However, there are 2 primary advantages to using train-test split instead of cross-validation. First, train-test split runs k times faster than k-fold cross-validation, since k-fold cross-validation essentially repeats the train-test split process k times. This is an important consideration for larger data sets, as well as models that take a long time to train. Second, it's much easier to examine the detailed results of the testing process from train-test split. As you'll see below, Scikit-learn makes cross-validation very easy to implement, but all you get back are the resulting scores. This makes it difficult to inspect the results using a confusion matrix or ROC curve, which are tools for model evaluation, whereas train-test split makes it easy to examine those results. Before we walk through some cross-validation code, I want to present 2 recommendations for the use of cross-validation. First, we've been using the value k equals 5 for our examples, and in fact any number can be used for k. However, k equals 10 is generally recommended because it has been shown experimentally to produce the most reliable estimates of out-of-sample accuracy. Second, when you use cross-validation with classification problems, it is recommended that you use stratified sampling to create the folds. This means that each response class should be represented with approximately equal proportions in each of the folds. For example, if your dataset has 2 response classes, ham and spam, and 20% of your observations were ham, then each of your cross-validation folds should consist of approximately 20% ham. Thankfully, Scikit-learn uses stratified sampling by default when using the cross-val score function, which is what we'll use below, and thus you don't need to worry about implementing stratified sampling yourself. Let's now go through an example for how cross-validation can be used in Scikit-learn to help us with parameter tuning. We're again using the iris dataset, and our goal in this case is to select the best tuning parameters, also known as hyperparameters, for the k-nearest neighbors classification model. In other words, we want to select the tuning parameters for k and n, which will produce a model that best generalizes to out-of-sample data. We'll focus on tuning the k in k-nearest neighbors, which represents the number of nearest neighbors that are taken into account when making a prediction. Note that this k has nothing to do with the k in k-fold cross-validation. Our primary function for cross-validation in Scikit-learn will be cross-val score, which will import from the sklearn.crossvalidation module. We're going to try out the value k equals 5, so we instantiate a k-neighbors classifier model with the n-neighbors parameter set to that value, and save the model as an object called knn. Note that we didn't have to import k-neighbors classifier because we already imported it previously. We'll now use the cross-val score function, giving this function 5 parameters. The first parameter is the model object, knn. The second and third parameters are x and y, meaning our feature matrix and response vector. It's very important to note that we are passing the entirety of x and y to cross-val score, not x-train and y-train. As we'll discuss below, cross-val score takes care of splitting the data into folds, and thus we do not need to split the data ourselves using train test split. The fourth parameter is CV equals 10, which means that we want it to use 10-fold cross-validation. The final parameter is scoring equals accuracy, which means that we want to use classification accuracy as the evaluation metric. There are many possible evaluation metrics, so I recommend that you always explicitly specify which one you want to use. You can see the complete list of metrics in Scikit-learn's model evaluation documentation, which I've linked to in the resources section below. Before we run this code, let's discuss what the cross-val score function actually does and what it returns. Basically, cross-val score executes the first 4 steps of k-fold cross-validation. It will split x and y into 10 equal folds. It will train the knn model on the union of folds 2 through 10, test the model on fold 1, and calculate the testing accuracy. Then it will train the knn model on the union of fold 1 and fold 3 through 10, test the model on fold 2, and calculate the testing accuracy. And it will do that 8 more times. When it's finished, it will return the 10 accuracy scores as a NumPy array. In our code, we're going to save that NumPy array as an object called scores, and then print it out. We can see that during the first iteration, the model achieved a testing accuracy of 100%. In the second iteration, the accuracy was 93%, and so on. As mentioned above, we'll usually average the testing accuracy across all 10 iterations and use that as our estimate of out-of-sample accuracy. It happens that NumPy arrays have a method called mean, so we can simply print scores.mean in order to see the mean accuracy score. It turns out to be about 97%. Because we used cross-validation to arrive at this result, we're more confident that it's an accurate estimate of out-of-sample accuracy than we would be if we had used train test split. Our goal here is to find an optimal value of k for knn, which we set using the n-neighbors parameter. Thus, we will loop through a range of reasonable values for k, and for each value, use 10-fold cross-validation to estimate the out-of-sample accuracy. We first create a list of the integers 1 through 30, which are the values we'll try for k. Then we create k-scores, which is an empty list in which we'll store the 30 scores. We use a for loop to loop through the values 1 through 30. During each iteration of the loop, we instantiate kneighbors classifier with nneighbors equal to the selected k value. We run tenfold cross-validation with that model. And finally, we append the mean accuracy to the k-scores list. Let's run this code and print the results. These numbers are a bit difficult to scan through visually, so we'll use a line plot with matplotlib in order to visualize how the accuracy changes as we vary the number for k. The maximum cross-validated accuracy occurs at k equals 13 through k equals 20. The general shape of the curve is an upside-down U, which is quite typical when examining the relationship between a model complexity parameter and the model accuracy. As I mentioned briefly in a previous video, this is an example of the bias-variance trade-off in which low values of k produce a model with low bias and high variance, and high values of k produce a model with high bias and low variance. The best model is found in the middle because it appropriately balances bias and variance, and thus is most likely to generalize to out-of-sample data. When deciding which exact value of k to call the best, it is generally recommended to choose the value which produces the simplest model. In the case of k and n, higher values of k produce lower complexity models, and thus we'll choose k equals 20 as our single best k and n model. So far, we've used cross-validation to help us with parameter tuning. Let's look at a brief example to demonstrate how cross-validation can help us to choose between different types of models. Specifically, we want to compare the best KNN model on the IRIS dataset with a logistic regression model, which is a popular model for classification. First, let's run tenfold cross-validation with the best KNN model to see our accuracy. As we saw above, the accuracy is 98%. Note that instead of saving the 10 scores in an object called scores and then calculating the mean of that object, I'm just running the mean method directly on the results. We'll compare this with logistic regression by importing and instantiating a logistic regression model, and then again running tenfold cross-validation. This gives us an accuracy of 95%, and so we would conclude that KNN is likely a better choice than logistic regression for this particular task. Finally, let's check out how cross-validation can help us with feature selection. If you remember the advertising dataset from the last video, you may recall that we were using linear regression to predict sales. One question we had was whether to include the newspaper feature in that model. We start by importing pandas, NumPy, and linear regression, and then reading the data into pandas. We'll first try a model with all three features. To build our feature matrix X, we create a Python list of feature names and then use that list to select just those columns from the data frame. We also select the sales column as our response vector Y. We instantiate the linear regression model and will again use cross-val score for cross-validation since it works with both classification and regression models. We can't use accuracy as our evaluation metric since that's only relevant for classification problems. We want to use root mean squared error, but that is not directly available via the scoring parameter, so we'll instead ask for mean squared error, and then later take the square root. Anyway, let's run tenfold cross-validation on our model and examine the scores. This doesn't seem right. If you remember the formula for mean squared error from the last video, you'd agree that the results should be positive numbers and all of these numbers are negative. What happened here? It's complicated to explain, but it boils down to the fact that classification accuracy is a reward function, meaning something you want to maximize, whereas mean squared error is a loss function, meaning something you want to minimize. There are other scikit-learn functions that depend on the results of cross-val score, and those functions select the best model by looking for the highest value of cross-val score. Finding the highest value of a reward function makes sense for choosing the best model, but finding the highest value for a loss function would select the worst model. Thus, a design decision was made for cross-val score to negate the output for all loss functions, so that when other scikit-learn functions call cross-val score, those functions can always assume that higher results indicate better models. If you found that confusing, you're not alone. There is a long discussion of this issue in Scikit-learn's GitHub repository that has been going on since 2013, which I'll link to in the resources below if you want to read further. This behavior is likely to change in a future version of Scikit-learn, but for now, we just need to work around this issue. The workaround is simply to take the negative of scores and store it in MSE scores. We'll convert mean squared error to root mean squared error by taking the square root. Finally, we'll calculate the average root mean squared error across the 10 cross-validation folds. Thus, we would estimate that the out-of-sample root mean squared error for this model would be 1.69. Our goal here was to compare the model including newspaper with a model excluding newspaper, so let's create a new X that only includes the TV and radio features. We'll compute the average root mean squared error in a single line this time by using cross-val score, taking the negative, taking the square root, and then taking the mean. The resulting estimate is 1.68. Since this is a lower number than the model that included newspaper, and root mean squared error is something we want to minimize, we would conclude that the model excluding newspaper is a better model. To wrap up, I want to briefly go through some common variations to cross-validation that are likely to make it an even better procedure. The first is repeated cross-validation, in which k-fold cross-validation is repeated multiple times with different random splits of the data into the k-folds, and the results are averaged. This provides a more reliable estimate of out-of-sample performance by reducing the variance associated with a single trial of cross-validation. The second improvement is to create a holdout set. Instead of running cross-validation on the entire dataset, a portion of the data is held out and not touched during the model building process. The best model is located and tuned using cross-validation on the remaining data. At the end of this process, the holdout set is then used to test the best model. The performance on this holdout set is considered to be a more reliable estimate of out-of-sample performance than the cross-validated performance, since the holdout set is out of sample for the entire process. The final improvement is for all feature engineering and selection to take place within each cross-validation iteration. Performing these tasks before cross-validation does not fully mimic the application of the model to out-of-sample data, since those processes will have unfair knowledge of the entire dataset, and thus the cross-validated estimate of out-of-sample performance will be biased upward. As such, a more reliable performance estimate is generated when these tasks only take place within the cross-validation iterations. Obviously, all of these procedures add some amount of complexity to your modeling process or your modeling code, and may also be computationally more expensive. Depending upon the particular problem, the benefits of using these improved procedures may not be worth the costs, so ultimately it's up to you whether or not simple k-fold cross-validation is good enough for your application. The proper application of cross-validation is a deep topic, and so ultimately there's no way for me to offer universal advice that applies to all situations. I've got a lot of great resources for you this week. First is Scikit-learn's documentation on cross-validation, which goes into many different cross-validation strategies, including how to build your own cross-validation iterator. There's also the documentation on model evaluation, which covers many different evaluation metrics, including advice on when and how to use each metric. If you're interested in the discussion behind why cross-val score returns negative values for mean squared error, check out this issue in Scikit-learn's GitHub repository. For a bit more depth on cross-validation at a conceptual level, read section 5.1 of an Introduction to Statistical Learning and watch the 2 related videos. Scott Fortman Rowe, author of the excellent article on the bias variance trade-off that I mentioned in a previous video, has another good article which compares adjusted R-squared, AIC and BIC, train test split, and cross-validation as estimates of model performance. Machine Learning Mastery has a friendly introduction to feature selection, which provides some good general advice and touches on the issue of doing feature selection within each cross-validation iteration. There's also a great IPython notebook from Harvard's data science class, which demonstrates how feature selection within cross-validation iterations is important when the number of features is significantly larger than the number of observations in your dataset. Finally, I've linked to a readable paper that examines many different variations of cross-validation in detail and argues for repeated cross-validation, among other recommendations. Thanks so much for your feedback on the last video, in which I asked whether I should cover more pandas functionality or just focus exclusively on Scikit-learn. The majority of you asked that I focus on Scikit-learn, but introduce useful pandas functionality as needed, so that's what I'll do. In the next video, we'll discuss how to search for optimal tuning parameters in a more automatic fashion. Until then, I look forward to your comments and questions. Thanks as always for watching, and please subscribe on YouTube if you'd like to be notified when my new videos are released.